My name is Bernadette Bucher from the GRASP Lab at University of Pennsylvania, and I will present my joint work with Karl Schmeckpeper, Nikolai Matni, and Kostas Daniilidis, Action for Better Prediction. In this work, we present a model-based approach to incentivize exploration via an adversarial curiosity objective. Our method can mathematically integrate with many approaches to prediction and planning by choosing to take actions which minimize the score from a discriminator for trajectories formed from states, actions, and predicted future states. In our experiments, we integrate our method with a video prediction model and the cross-entropy method for planning, which form a commonly used pipeline for vision-based robotic control. This application highlights the increased computational efficiency of our curiosity approach, aiding its effectiveness in continuous high-dimensional settings on physical robot platforms. The pipeline in which we integrate our new discriminator method for curiosity is commonly known as planning from pixels. To accomplish manipulation tasks, goals are specified by human-designated start and goal pixels on an image. Then, the cross-entropy method is used to select actions to move from the start to goal state. The cross-entropy method samples actions from probability distributions approximated by how close the action will bring the robot to the goal state. The sampled actions are evaluated using a pre-trained video prediction model to determine which action selection results in a prediction closest to the goal image. As opposed to accomplishing a manipulation task, the goal of our variant to this pipeline is to sample the environment in order to find data which can be used to improve our prediction model. First, the video prediction model we use is pre-trained jointly with our discriminator. Then, the sampled actions are drawn from a probability distribution approximated by how unrealistic the resulting model predictions are based on the discriminator scores. The sampled actions are evaluated using the discriminator, and the most unrealistic action sequence is taken. We hypothesized our curiosity method would yield performance gains in the inherent domain transfer task this robotic control pipeline faces by using publicly available datasets for pre-training the prediction models. In particular, the datasets available to pre-train the prediction models are not collected in the same lab environment under the same conditions, and not always even collected on the same robot platform as that of the target control experiments. However, using these datasets is important since requiring data to be collected from scratch on every target platform would be computationally intractable as a long-term solution. Currently, when leveraging these datasets, the prediction models are first trained offline on a dataset of robots taking random actions in a bin of objects. Next, a small collection of data is gathered of robots taking random actions in a bin of objects on the target platform. The data is used to fine-tune the pre-trained prediction model before the model is ultimately used to execute tasks. We propose an enhancement to this pipeline in which the samples used for fine-tuning the prediction model are collected via curious instead of random sampling. Specifically, in our experiments, the prediction model is pre-trained jointly with the discriminator on Sawyer robot videos in the publicly available RoboNet dataset. The discriminator is then used for action selection with the cross-entropy method to collect data on the target Baxter robot platform. This data is used to fine-tune the prediction model, which is then used to execute tasks. We present three main results regarding the performance of our method for this robot learning problem. First, curiosity increased object interaction in the data collected for fine-tuning. We measured object interaction by non-zero finger force records from Baxter's grippers, which indicate instances in which objects are grasped. Curiosity also increased exploration of the state space with more complex dynamics. In particular, the robot interaction data is collected in a bin of objects, and the contact dynamics of the objects with the edges of the bin is both complex and not modeled well by video prediction methods. More samples are collected in these areas of the state space with our curiosity approach, as measured by discretized visit counts. Finally, fine-tuning the prediction model with samples collected with our curious policy resulted in statistically significant improvement in prediction error of the model during control task execution. We plot the prediction error improvement with different quantities of samples used in fine-tuning and find the improvement is most pronounced when lower numbers of samples are used to fine-tune. In future work, we plan to include task completion results for our robotic experiments. We also plan to evaluate our method against other curiosity approaches in a less complex experimental setup, since existing curiosity methods are not computationally tractable for this robotic control pipeline. Thank you very much for your time and attention, and we look forward to any comments or questions.